Metamorphic rocks. The root morph means to change, like metamorphism of a tadpole into a frog, metamorphism of a caterpillar into a butterfly, or the Mighty Morphin Power Rangers, if you ever saw that cartoon where they morphed and they changed into something else. So a metamorphic rock is a rock that has changed from one thing into something else because of heat and pressure. It needs high temperatures and it causes the minerals to shift around and to recrystallize, a process called recrystallization. This is an example of a metamorphic rock, schist, where you can see these big chunks of garnet that have recrystallized. Originally the minerals were smaller, they have grown and gotten larger as the heat and pressure has caused this recrystallization. The rock that you started with originally is referred to as the parent rock. Right? The parent rock gets heated and pressurized and it changes into a metamorphic rock. Just like a parent, right, can then lead to offspring or babies, parent rocks can lead into metamorphic rocks. Any type of rock can be a parent rock. Sedimentary, igneous, metamorphic, it doesn't matter as long as that rock is exposed to the heat and pressure. So even metamorphic rocks can get metamorphosed into other metamorphic rocks. So there are lots of different kinds of parent rocks. And again, that causes the recrystallization of those minerals to grow larger. Next, where does this happen? This usually happens deep underground. That's where you get the heat and pressure that is necessary in order for metamorphism to take hold. So if you look at a cross-section of the earth, here's a volcano, this is the surface, the ground, this is like the ocean or a lake, this is the water. Go deep underground, you're going to find areas where there is high pressure and high temperatures that can change those rocks, recrystallize those minerals, cause those crystals to get larger. There can also be places where there's heat, and we'll talk about that as well. Example of metamorphic rock. Perfect example is slate. Right? Slate is a hard version of shale. Shale, if you remember from sedimentary rocks, is that one that was layers, it's very crumbly, it broke in your fingers, it's very soft. But if shale is heated and pressurized, it turns into the metamorphic version, which is called slate. Shale turns into slate. Here's an example of green slate that I got from Juneau, Alaska. It's really hard, it's dense. If you feel it, it will not crumble in your fingers like the shale did. So good indicators that a rock is metamorphic. It could be dense, it could be very hard like that slate. If it had pores, it doesn't have pores anymore. It becomes less porous because the pressure squeezes those out. Distorted structure. Here's a neat picture of distorted structure. If there's bands and bends to it, if it's twisted, the layers are all messed up, that tells you that the pressure has changed that and caused some shift. And if you get crystals that are larger from that recrystallization. Very important type or indicator for metamorphism, the letter B in your notes, is foliation, a foliated rock. Foliation is the definition. It's when the minerals separate or align themselves into bands, commonly referred to as banding. So the pressure is on the rock that causes the minerals to kind of group together based on their properties. So a very good example of a metamorphic rock is gneiss that has banding, and if you look closely at this rock, you'll see that there are black bands where biotite and the darker minerals are banded together from that heat and pressure that was exposed to it. And you can also see pink bands where the feldspar, potassium feldspar, has come together. The thicker the bands, the greater the degree of metamorphism. So this rock right here has had a large amount of heat and pressure, whereas this one right here that has banding, yeah, there's been exposed to heat and pressure, but not so much. And a couple other examples of banding. Here's a core sample taken from Gouverneur, New York in the Adirondacks, where they drilled out the rock. And if you look at it, you can see the pink feldspar minerals that have banded together, and actually they're a little distorted, right, from the heat and pressure that form the Adirondack Mountains. And here's another look, smaller core sample that they drilled out. But again, if you twist that and you look at it, you can see the bands in that metamorphic rock. So banding foliation is a really good example. The thicker the bands, the higher the degree of metamorphism. On your reference tables under texture, you can see where they identify rocks that have banding, and that rock is called gneiss. Notice how it's spelled with a G. So the examples that I showed you of the core samples and this one right here, these are all examples of gneiss that have really thick bands. There are other foliated rocks that don't have as large a degree of banding. They are listed here under foliation or mineral alignment. And what they're saying is as you go down, the heat and pressure increases, so you get thicker and thicker bands, and they're all different types of foliated metamorphic rocks. The non-foliated metamorphic rocks are much harder to distinguish because they don't have any unique properties like banding that stick out with your eye. And that's because the pressure is coming on from all different directions. A good example of non-foliated metamorphic rock is marble. When you look at it, yes, it's hard, it's durable. That's how they can use it for statues and such. But it doesn't have any unique pattern to it. It's the same all the way throughout. Another example is quartzite. Quartzite, if you look closely at it, you don't see any bands, you don't see anything unique about it, but it is very hard, it's a very durable, very dense rock, and that is from the pressure. The non-foliated rocks and reference tables, again under texture, highlighted on the bottom, there are 5 different types. The first one's anthracite coal that comes from the sedimentary type of coal. If you remember touching the sedimentary type of coal, it was brittly and crumbly. Anthracite coal is a lot harder, so it's harder to break pieces off. And you can see it's shiny. That's from the recrystallization. Anthracite coal. Hornfels, quartzite I just showed you a sample of in marble. And then metaconglomerate, which used to be conglomerate, but the heat and pressure has stretched and distorted the pebbles, so they're kind of twisted a little bit, distorted. That's metaconglomerate. On the bottom of the page, there are 2 types of metamorphism that you have to identify. The first is contact, also referred to as thermal metamorphism. The word contact means to touch. So in this case, you look at the definition, it's where the heat from something has touched another rock and changed it. And that something is usually molten magma or lava. So here's a good example of my contact metamorphism. If I take this rock right here that I got in the Adirondacks, it was a green rock buried deep down underground. There was a crack in the rock, and it actually was a lot larger than this. There was green rock over here, green rock on the side, and there was a crack in the middle. In that crack, the heat and magma moved up through. And when that was hot, that heat on either side, the right side and the left side, touched that rock and changed that rock. So this maybe used to be igneous or sedimentary. It got changed into metamorphic rock. This here, the white, used to be liquid. So what kind of rock is formed from liquid or molten material? Good, igneous. So what you see here is you got metamorphic, igneous, and then another type of metamorphic rock. So that is called contact metamorphism. It usually happens over a small area, right where that lava or magma is touching the surface, or touching the other rocks, and it happens nearby veins, like where that magma, that white vein of igneous rock is cutting through. Notice the rocks are not cooked, not melted, they're just kind of heated up and changed. Any rock can undergo contact metamorphism as long as you have a large enough amount of heat. And something called a transition zone is where that heat has changed the rock into metamorphic, but as you get further away, there's not enough heat, and it transitions back into the original parent rock, the original parent type. That's contact metamorphism. On the next page, there is a diagram that I'm going to want you to write 1 or 2 sentences to describe how that diagram was formed. It's basically similar to mine. What you should see is there is an igneous intrusion or a vein where that molten material was cutting through. Now, how my picture differs from yours in the notes is mine has a fault that broke it or split it. So once it gets to here, you can see where it had originally continued before it got broken. So find that igneous intrusion, that igneous vein in your picture. What that represents, and I just colored in red, is that's where the hot lava, or hot magma, in this case, was moving through the rocks. And as it moved through, you're going to see these little marks on the side that I will color blue. And yes, they look like the little hairs on a caterpillar. What they are is they are the contact metamorphism marks. So they represent where that heat was touching the other rocks and changing them. So as I go ahead and add these in right here, what you can see is it's touching these other layers. Well, what type of rock is in layers? Yes, sedimentary. So what that tells me is like right over here where this green X is, that is a sedimentary rock. But right over here, if I put a green little star, that is not sedimentary rock anymore. That is metamorphic rock where the heat and pressure changed it. So there's a transition zone here from sedimentary to metamorphic from the contact metamorphism. And then what I'm going to show you in just a little bit, how this sedimentary rock right here at X, according to the key, is limestone, but then when you get to the star, what you'll see is limestone gets metamorphosed into marble. So you can tell where the marble is, you can tell where the limestone is, and we'll use the reference tables to identify that. That's contact metamorphism. So make sure, if you have to, you pause it, and you write a couple of sentences describing that diagram. Second type is regional metamorphism. The word region means over an area. So if your basketball team is good enough to make regionals, or your dance team, you're the best for the whole region, the whole area. So now you have pressure that is over a large area that is changing the rocks. That typically happens when continents collide or big chunks of plates collide into one another. And when that does happen, it's associated with something we call orogeny, or mountain building. That pressure causes the rocks to change, they get metamorphosed, and they get pushed up, and they create mountains. So the best example for us in New York State is the Adirondack Mountains, which is not too far away, where the pressure changed those rocks and pushed them up. That's why so many of my samples have come from the Adirondacks. Regional metamorphism. On your reference tables, if you look in the middle of the chart, you'll see the type of metamorphism. So you can see up here, regional, slate, phyllite, schist, and gneiss. All of those are formed from the pressure of regional metamorphism. And they're telling you as you go down, the heat and pressure increases. Regional metamorphism is also how anthracite coal is formed. And then the bottom three, quartzite, marble, and metaconglomerate, can be formed by regional or contact. Hornfels is the only metamorphic rock that is solely formed by contact metamorphism. Using your reference tables, you can figure out which parent rocks will turn into particular metamorphic rocks. For example, I already told you that shale turns into slate. Sandstone, when it gets metamorphosed, turns into quartzite. It's that limestone that I showed you in the diagram that gets metamorphosed into marble, same as dolostone. Conglomerate gets turned into metaconglomerate. That's pretty easy to match up. And granite, like I was showing you with the gneiss, right? This gneiss used to be just crystals of granite before it got metamorphosed. There are different metamorphic rocks that can be formed from the same parent rock. It depends on how much pressure and heat are exposed, so it depends on the conditions. And the best example is up here, how you can start with shale, and yes, it can get turned into slate, but it can get turned into other metamorphic rocks based on how much heat and pressure you apply. And then that's the last thing we have to finish up. So here's an example. Again, putting the pressure on that rock to form banding depends on the degree of metamorphism. Let's start with shale. This is what it would look like under a microscope. You don't see any alignment. Add some heat and pressure, and it causes a little bit of alignment from that low-grade metamorphism. You get slate, much harder, more durable rock. If you add more heat and pressure to slate, it can turn into something else. Actually, it turns into one called phyllite, which there's no picture here. Phyllite can turn into schist, which now is much more aligned because of the heat and pressure. And schist can turn into gneiss, where you see really thick bands because of the high degree metamorphism. You do not need to memorize this section of notes, because on your reference tables, it is showing you that if you look at regional metamorphism, as you go down, the heat and pressure increases. So as you go down, start at the top of the chart. Low-grade metamorphism of shale. Well, shale gets turned into slate, like I just showed you my example from Alaska. Slate, if more heat and pressure go down, it turns into phyllite. Phyllite turns into schist. And schist, if you have lots and lots, high-grade metamorphism, lots of heat and pressure can turn it into gneiss. So there are a couple of different ways to make gneiss based on the heat and pressure. And last but not least, on the bottom of page 8 in your notes, there is A, B, and C about rock distribution types. You now learned about sedimentary, igneous, and metamorphic. So if you can answer those 3 questions based on what you already know, and we can go over those tomorrow.